And today I will talk to you about scalable coating techniques for industrial compatible perovskite solar module fabrication. So basically, during these years of research on perovskite, a lot of claims, during the paper reading and so on and so forth, there is this phrase from lab to fab. But when, especially, because the scaling up of perovskite is general, really not so relevant in the research paper area, at least for, it's not well covered, let's say, or implemented like the material optimization that generally is presented in the major part of the articles. But the upscaling can, let's say, have can introduce, let's say, a number of complexity that is related to the process transfer, for example, or to the environmental restriction for the sensible material in the standard condition that we might, let's say, desired for scale up our technology. That could be, for example, room temperature or relevant relative humidity above 13%. And also the material toxicity. It's another important point to address in this case for transfer the processes from the lab to the fab. And moreover, the stability on the device and on the modules especially, because the processes to get modules are more than to get a cell, obviously. And for example, P1, P2, P3 laser process can be a first source of instability in the device if they are not well done, as well as the uniformity that of the all the layers that are done on the larger substrate due to the technique that we choose that cannot be direct transferred from the spin coating process to eventually blade coating, slow die coating, or inkjet printing, for example. Also, another kind of instability, another source of instability for the modules could be the reverse bias. In this case, when we put more cells in series connection. So to address this kind of answer, I will show you two kinds of formulation that were used and scaled, let's say transferred from the spin coating glove box environment to blade coating techniques or slow die coating technique in ambient air with relative humidity up to 30%. So these two formulations are respectively the triple cation perovskite 1.63 eV. We have also a study on the low temperature ETL in order to get a bigger module on the bigger size. And also we perform with this kind of perovskite a demonstrator for a tandem application. Then we will move to a narrow band gap perovskite study and upscaling, in this case a cesium fab perovskite. And also another way to get this kind of perovskite from a different source of precursors, okay? And then the outlook and conclusion. So, starting with the triple cation perovskite upscaling in ambient air, I just show you briefly our stack configuration. In this case, this was the mesoscopic structure, NIP structure with compact and mesoporous TiO2, the perovskite, spiro, and the gold electrode. All the processes that are let's say used to make the device are all in ambient air, except for the gold evaporation, of course. And we develop and optimize deposition of the perovskite that counts 5 steps. Basically, we have the precursor solution deposition with a preliminary drying step with an air knife, and then we deposit our green antisolvent, that is in this case isopropanol, isopropyl alcohol, coupled again with the air knife to get to force the crystallization of perovskite and the conversion step, and then the annealing. With this kind of configuration, we were able to coat substrate that are 5.6 by 7.5 centimeter, and to get from this device, from this substrate, an array of small cells in order to assess not only the uniformity through the different optical measurements, but also a number, let's say an efficiency and the photovoltaic parameter for each zone, and then we transfer them to mini modules area. Here I will show just a comparison between the mini modules that we produce, and we did them in spin coating with the spin coating in a nitrogen environment and with the blade coating in ambient air, as I already presented to you. You can see, even if the PCE is, let's say, not in the state of the art, but the gain in the efficiency is more relevant for the ambient air blade coated perovskite, and also the analysis that we did on this kind of modules can clearly highlight that the spin coating is not our let's say a technique for large areas, because the centrifugal force together with the Comet's effect can of course produce defects, more defects on larger area respect the blade or the slow die, as also the EL images can attest here. And of course this is reflected also in the stability, in the operational stability in this case, that is also quite enhanced for the ISO's test L1 for the light soaking. Okay, once we got, let's say, an efficiency that is comparable with our nitrogen spin-coated device, we move to the optimization of the ETL. In this case, we need low temperature ETL, because to get larger and larger substrate and, of course, larger module, you want to avoid, of course, a high temperature process like compact TiO2 with the spray pyrolysis and calcination of TiO2 at 500 degrees, that, of course, are not only not favorite process for an industrial for the industry for the energetic cost, but also the high temperature can just crack your substrate and you have just to redo from the start. So I will just go quickly through the optimization of this ETL, that is just tin oxide nanoparticles in water, dispersed in water. The stack is the same, the process is the same, and the substrate will be the same. But in this case, we just move to large area substrates, large area cells, sorry. So at the end, for each piece of glass, we will have 4 cells of 0.5 centimeter square active area. We optimize several parameters like speed of the plate, the temperature of the plate, temperature of the air, concentration, speed of the height of the blade, and with this kind of optimization, we got a compact and uniform tin oxide ETL at low temperature, below 160. We just annealed them at 150 in ambient air with a peak efficiency above 17%. So once we got all the stack made in ambient air and the low temperature for the wall fabrication, we just move to bigger area basically, and in this case we go to sub-module device. In this case we move to 32 centimeters square substrate, that is the area of the mini module, to 10 times this one, for an active area of 180 centimeters square and an aperture area that is major than 200 centimeters square, which is, let's say, the range in which the substrate can be let's say called sub-module. I will show you briefly just the position of the perovskite that I already explained you. So as usual, we have the deposition of perovskite solution coupled with the hair knife to pre-dry the film, and then we did the same thing with the annealing with the anti-solvent process, sorry, to get this mirror-like uniform and shiny perovskite layer. Of course, the optimization from small to large area, in this case, even we don't change, let's say, the environmental environment and the technique is not so easy. I will just report you the main steps that we got on this scaling up. So as you see, the first scaling up, it's give us quite poor module efficiency, just up to 7.8%, and then we start to process engineer basically, so optimizing the machine parameters due to the substrate side, so height of the blade, speed of the plate, amount of material, the airflow, the temperature of the airflow, so on and so forth. So this kind of adjustment, of course, boosts the perovskite crystallization on the wall area and give us, let's say, the first jump of efficiency from 7.8 to 12.5%. We also characterize, of course, this kind of optimization from optical point of view and also morphology point of view. The next step instead was just implementing the passivation on top of this kind of material. So we just use phenethylammonium iodide as a reference passivator that enable the formation of 2D perovskite on top of the 3D perovskite and passivate the grain boundaries and basically boost our VOC. And the passivation strategy, we got the best efficiency around 13.4%. And we also obviously assess the presence of the 2D perovskite on top. And we see also the passivation effect of our PI molecule on top of our perovskite. Last step of our optimization, in this case for the wide bandgap perovskite, was the perovskite solution tailoring. So we start to we add a certain amount of acetonitrile in our DMF-DMSO solution mixture in order to have an high vapor pressure non-coordinating solvent for the fast formation of the metaphase of perovskite. So the phase in which the perovskite, let's say, starts to seeds and start basically to start the crystallization. The addiction of ACN is due to a couple of reasons, because the first one is that we want an evaporation rate that is uniform on the wall area. And the second thing is that we want milder condition for the quenching of our film, especially for the hair blade, because in this case, the size of the blade of the module was really close to the limit of our machine. So we need to put lower pressure in our hair knife just to do not have strange effects on the film, due actually to the exposition of the first part of the film that we have at the start of the deposition respect to the end one that just have, let's say, experiment the hair in just that amount of a small amount of time respect to the first one. So implementing the perovskite solution tailoring together with the process engineering that I showed you before, the best efficiency that we got for our modules with 180 centimeters square of active area is attested at 14.5%. So I show you the first optimization with the process engineering. The second one choose the passivation on the surface of our 3D perovskite, and then the solution tailoring of the perovskite, merging all of them together. The optimized process and materials together with the passivation have a synergic effect on the photovoltaic parameter, boosting the efficiency of the best module that we got at 16.05%. That is quite huge for this kind of size. We obviously assess the uniformity of this module with different techniques, morphology techniques, and also EL measurement to understand visually on the modules where and how the cells behave. And of course, also the stability is something that we addressed. This kind of fabrication, we also use this kind of fabrication to have a life cycle assessment analysis. And of course, the first, the most impactful process for NIP structure in this case is the cold evaporation, of course. First, for the high cost of the raw material, and also for the high cost of the process with the high vacuum evaporation. Of course, also the low temperature ETL impact less than the high temperature ETL, and for this reason also for the let's say, to avoid the gold electrode, we also tried some ITO electrode, in this case on 15 by 15 substrate, in which we fabricate 110 centimeter square active area module. We tried with gold, with ITO, and we also tried with four terminal tandem configuration with silicon, just as a demonstrator. As you can see, if we use gold, of course, the PC is around the best PC that we got also on the other substrate, around 16%. With ITO electrode, we are around 13%. And another, with the silicon, the module is not really optimized, let's say, also electro-optically to at that time to get really high efficiency. So practically we got the same efficiency of silicon alone, but it's okay. It was just as a demonstrator. The important thing is the stability that we got on this semi-transparent module, because the T80, in this case for the wall stack made in ambient air with 30% of relative humidity, reached his T80 after 1,200 hours. That is quite good, let's say. After this, we just moved to narrow bandgap perovskite, and also because narrow bandgap became, let's say, more important during this year of research. And we also evaluate the performances of this narrow bandgap perovskite from a different precursor source. So of course, is obvious that changing the content, with the Fa content in the perovskite ink affect the phase transition. Maybe perovskite is prone, let's say, to give alpha phase quite easily, where FAPI not. And for this reason, of course, we have to optimize the spin parameters and regulate the crystallization. As usual, we start with the glove box spin coding way, and the perovskite that we use in this case, it's a narrow band gap 1.55 EV with 5% of cesium and 10% of methyl ammonium. We also implement the passivation strategy here on top of the 3D perovskite. And with this kind of system, optimizing, let's say, all the parameters in order to get a good crystallization of our perovskite layer, we got the best efficiency in a small area, above 20%, and for the best mini module, above 19%, respectively. So once we got the good results on the glove box, it's time just to forkot it, because we go to ambient air. We like blade, not to spin. And in this case, the stoichiometry of the formulation is a little bit changed. We use a little bit more of cesium. We increase the cesium content that can act as a seeding site and help the crystallization in the blade coating techniques. And we just avoid methyl ammonium in general, but we use only as additive, as usual, like methyl ammonium chloride. We did several trials with this kind of perovskite to get a good crystallization, and several concentration are also tested to get the right thickness of our perovskite, with an efficiency between 14 and 15% for the first trials. Then we move this kind of formulation in a pre-synthesized cesium FAPI powder. This means that basically we already react all the precursors in a mild environment, in a mild solvent medium, in this case ACN. We use also low purity lead iodide precursor, the just 99% from Sigma, and not the high purity lead iodide from TCI, for example. And with this kind of process, we can make a batch of FAPI powder from low purity precursor, basically, with a yield measured at 93%. And these kind of things is also in an optic that can avoid, let's say, weighting mistakes, because when we weight all the powders from high purity precursor, for example, we always can have an error, on a human error, or let's say an instrumental error, that can give us maybe an abundance of lead, or an abundance of cations that could be detrimental for the perovskite layer stability and also crystallization. So basically what we did is we just put the cations in ACN, we make them reacting with the lead iodide at low purity for 24-48 hours at room temperature. Then we filter off all the crystals that in this case that are in delta phase, and then we have the conversion in an oven to the alpha phase. Once we got these crystals, they are already in alpha phase. They are stable for months in an inert environment and can be just weighted as a normal powder. Then, obviously, we can use our solvent system to get the ink solution. So we study a little bit the film that comes from this Fabi powder precursor solution, and it's obviously, and our control in this case is the cesium Fabi from high purity precursors. What we saw morphologically is that the films made from the Fabi powder has less phenols, as no unreacted species like this lead iodide that we can see for the high purity precursor case, and also the grains are much bigger. This trend is also confirmed by XRD analysis that show higher crystallinity for the perovskite peak, 14 degrees, and also the microstrain analysis that we did from the XRD show less strain in our perovskite lattice for the perovskite that comes from the powder method. Another peculiar things that we saw is doing dynamic light scattering measurement on the perovskite ink, on the two perovskite inks, show two different population. Let's say for the high purity precursor, we can see only one population peaked around 1 nanometer. That is, let's say, the dimension of the colloids present in the solution. But when we use to melt the cesium Fabi pre-synthesized powders in our solvent system, we have two different populations. The one peaked at 1 nanometer, as usual, and the other one peaked at 100 nanometer. So we speculate that, of course, the size of the colloid that are inside the solution can have an impact on the deposition and on the crystal quality, and especially for our process, this may behave in a good way to get let's say a nice film, a nice and compact film that melting only the high purity precursor do not. Passing through the devices, we just perform we just fabricate some cells, 0.5 centimeters square of active area, and here, even though let's say the record JV, the record devices have the same efficiency, more or less, even if it's a little bit more efficient, the cesium from the Fabi from powders, the means on the full photovoltaic parameter show us the reproducibility that is quite enhanced for the perovskite coming from the powder approach. With the narrower distribution of the parameters among the photovoltaic parameters, and this is let's say a result of a reproducible and also a more solid way to have a stoichiometric perovskite ink. We do other characterization to extend, let's say, this study. From SCLC analysis, we can see that, for example, the perovskite layer from powder has less trap density trapped state density that is also demonstrated by TRPL analysis, in which the slow component of the decay of our FABI perovskite from powder it's much lower than the high purity precursor film. In all the cases, we didn't lose any optical characteristics on the films, because even the UVBs and the PL steady state preserve the same peak without any shift. So the compositional part is controlled quite carefully, and also the stability is improved for our FABI from powders. The quite let's say in a good way for the ISOs test D1, that is the shelf life, and also for the light soaking test. Especially for the light soaking test, I don't know if it's really visible because it's a bit smaller, but let's say the T80 for our FABI powder comes like at 320 hours after the light soaking, and for our high purity precursor instead the T80 is just at 120 hours. It's still poor stability, let's say, but we continued the test till 1000 hour, and we saw that our FABI powder from 1000 hour at 1000 hour just lose less than 40% of its initial efficiency, where instead the high purity precursor lose more than 80% after 1000 hour. That is of course, are results. I have to also highlight that in the perovskite, in this case, there are no additives except for MyCl. So just to compare the films, the bare films as they are. Of course, focusing on the cesium FABI powder, we perform a mini module fabrication. Of course, P1, P2, and P3 process were optimized in order to get clean P2 and a good isolation between each cells with the P3 and P1, of course. And for this kind of module of 12.5 centimeters square active area and 5 cells interconnected, the best efficiency that we got is attested at 18.5%, really close, let's say, to the peak efficiency that we got on 0.5 centimeters square active area. We perform also a small cost evaluation for 1 gram of perovskite produced with the high purity precursor lead iodide, and the other one with the standard sigma 99%. And as you can see, even with the yield of the synthesis that is not 100% in the case of low purity lead iodide, the cost it's 1/4. It's like the cost of the let's say high purity perovskite. It's 4 times more than our perovskite made with low purity precursor. That is quite well demonstrated that it's not a big requirement, let's say, to get good and high efficiency. So to just conclude, our answer to perovskite scalability issue can be summarized in this bullet point. So we just implement a fully ambient air fabrication. We introduce green anti-solvent quenching. That it's something really important to scale on the let's say on a factory environment. We are also working, let's say, to replace the MF and the MSO for the same reasons. We optimize low temperature ETL, of course, uniformity and stability assessment as usual, and all the laser processes optimized. And also we tested low purity raw material that in terms of cost for future production, it's something that has to be let's say taught. So in the end, we start with our NIP configuration, high temperature NIP configuration. We move to scale first the perovskite from a spin coating glove box to the air, ambient air with the blade coating or slow die coating, and demonstrate practically the same efficiency between the glove box spin and the ambient air for the wide bandgap perovskite. We optimized also the narrow bandgap perovskite with an efficiency above 20 and 19% for small cells and for mini modules. And then we move forward to scale up with hybrid approach with the blade slow die coating up to 186 and 200 centimeters square of aperture area modules through process engineering and chemical engineering of our inks. With this, I want just to finish my talk and acknowledge all the people from my labs, my professor and supervisor Aldo Di Carlo, and of course the fans, and all of you for your attention. Thank you.